Hi there, in this video we're going to be looking at how to determine the Lewis electron dot structures for ionic compounds. And this isn't done very often. Usually we do this for covalent compounds. I'll have a different video explaining that. But for this one we're going to show how this works. And there's easier ways of doing this, but this way really explains what's taking place. So you have a really good understanding of why the atoms are doing what they're doing and why they end up with the charges that they end up with. All right, so the first thing we got to think about, though, with this is, or the rule that kind of governs this process is called the octet rule. The octet rule is the tendency of an atom to obtain an electron configuration with 8 valence electrons. Where those 8 valence electrons are coming from, that's 2 electrons in the s orbital and 6 electrons in the p orbital. So you need to understand how electron configurations work. We're looking at the outermost s and p electrons when we're looking at valence electrons. So again, where this number 8 is coming from is what we're doing is filling up the s and the p. S orbitals can hold a maximum of 2. There's only one s orbital, and p orbitals always come in sets of 3, and so they can hold 2 electrons apiece. That's where the 6 comes from. So a total of 8 electrons. So all elements typically are trying to gain or lose enough electrons so that they achieve that octet of electrons, 8 electrons in the valence orbitals. And so it's really easy to figure out how many valence electrons an element has. We can do that using the periodic table. And you'll notice I've written some stuff above the columns here in the periodic table. For example, all the elements in this first column have an s1 electron configuration. That's 1 electron in the s orbital, like hydrogen's a 1s1, lithium's a 1s2, I'm sorry, a 2s1, sodium's a 3s1, a 4s1 for potassium, and so forth. So they all have 1 electron in that valence orbital set. And so we just say there's 1 electron there. The column 2 here all have an s2 electron configuration, so just 2 electrons. We're not going to do this for the transition elements, we're just going to do this for the main group elements. So we continue over here to boron's column, and all the elements in boron's column have an s2p1 configuration. For example, boron has a 2s2, 2p1 electron configuration. That's a total of 3 electrons. 2 plus 1 gives me 3 valence electrons then for boron's column. So aluminum, gallium, indium, thallium, they all do that same thing, have 3 electrons in the valence. Carbon's column, they have 2 in the s and 2 in the p orbitals there, so a total of 4. We don't really care which orbital they're in, whether they're in an s or a p orbital. We just want to know what's the total number in that valence shell. It's just the outermost. It's not the total number of s and p, just in the outermost energy shell. And so all the elements in a column will have that same configuration then. And we just continue on. 5 for nitrogen's column, 6 electrons in the valence for oxygen's column, 7 for fluorine, and finally we get over to the noble gases here, and most of them have 8 electrons then, an s2p6. Again, that's that completely filled orbital set, which is really, really stable. The only one that doesn't is helium. Helium only has 2. For that, and so hydrogen kind of goes along with that. That's why I put this other little designation in here, that hydrogen only needs 2 electrons for a complete valence shell for that. So that's what we're doing with all of this. All right, and so what we're going to look at first is a fairly simple system. We're going to look at sodium and chlorine. I'm going to use a different color for chlorine just to kind of set it apart here. So we'll use kind of a green color for chlorine. Again, I'm just going to use single atoms for these. All right, so the first thing we want to figure out then is how many valence electrons each of these elements is going to have. And so for sodium, here it is in column 1, it's going to have 1 valence electron. So we show that just with a single dot in there. And chlorine is all the way over here in the second to last column. Again, that element, or that, all the elements in that column are going to have 7 valence electrons. Again, it's 2 in the s and 5 in the p is really where that's coming from, but we just care about the total here. So in that column, it's going to be a 7, and so we can fill in 1, 2, 3, 4, 5, 6, 7 valence electrons. And so we want to look at then how many electrons sodium can lose and how many electrons does chlorine need to gain to make everybody happy, essentially. Although the atoms can't really be happy, but we like to think of them as being happy. And so sodium obviously only has 1 valence electron to give up, and if it gets rid of that one, it'll be down to a completely filled orbital set, back to a noble gas configuration. The chlorine, on the other hand, it's just missing 1. It's kind of got an empty spot right here to fill. If we can fill that empty spot in, then the chlorine will be in a more stable configuration then, or I use the term happy for that. And so all that needs to happen here is that one electron from sodium is going to get donated, basically put over here onto the chlorine atom. So again, those are both neutral to begin with for this particular system. Sodium's going to give up that one electron, chlorine's going to take that one electron in, and that gives us our products then as a result of this reaction. When I write the symbol for sodium now, I'm just going to use an Na, and to show that it's lost that one electron, we'll give it a +1 charge then for that. And so I'm just not going to put any dots around that to, again, indicate that it's lost those electrons. For the chlorine, on the other hand, here's our chlorine, and again, I'll put in the 7 green electrons that it originally had, but now it's got that one extra electron from the sodium. So I'll use a black dot to represent that, just to show where it actually came from. Again, chlorine doesn't really care. They're all the same kind of electron there. There aren't different kinds of electrons. And so with that one extra electron in there then, that gives chlorine a -1 charge. And everybody's happy. Everybody's got their valence electrons, a more stable configuration. Sodium now has an S2p6 configuration since it lost that one electron that it started out with in its valence, and the chlorine gained that one electron, and its valence orbitals now are completely filled. Again, that's what's making these stable. All right, and so there's our product ions then. Again, if they're positive charged, we call those cations. See the nice little plus sign I put in the middle of that for the T? That's one easy way to remember that. And then the chloride ion, we call that an anion. Negative ions are negative charged ions. We call those anions. All right, let's take a look at one other example. Let's take a look at magnesium. And again, we'll look at chlorine as well with that. Just a little bit tougher system, but it's not too bad. All right, and so let's take a look at the periodic table once again. And here's magnesium. It's in column 2, so it's going to have 2 valence electrons. So we'll put 2 dots, 2 dots around the magnesium to show its valence. And I go back to my green marker here. For chlorine, same as what we had earlier. 1, 2, 3, 4, 5, 6, 7. And you can probably already tell something isn't going to work out right here. And so for this to happen, draw my arrow in here first. So just like we did with the sodium up here, magnesium can give up one of its electrons and put it over here onto the chlorine. And of course what that does is it satisfies the octet rule for that chloride ion. So we end up with our Cl with 1, 2, 3, 4, 5, 6, 7. I'll put my negative charge in there, green. And there's the electron from the magnesium. So that chlorine is all set when magnesium gives up one electron to the chlorine. But do you see the problem? Magnesium still has this other valence electron that it wants to get rid of. And so how this happens, remember, we don't ever just have one atom of each. We're going to have bunches and bunches of them. And so it actually takes a second chlorine atom. So let's draw another chlorine in here. And again, what we're trying to show is how many atoms of each element are necessary for complete reaction. Turns out one magnesium is not going to react with just one chlorine atom, but it takes a second chlorine to accept this other electron from the magnesium. Since magnesium's got 2 electrons to give up, but chlorine can only take in 1, it takes 2 chlorine atoms then to help out that magnesium and get that completely stable. So when magnesium loses 2 electrons, we end up with an Mg2+ charge. Again, it lost 2 electrons, so we'll show that with a +2 charge. And of course, then we end up with a second chloride ion with that accepted the other electron from the magnesium. All right, again, magnesium is the cation, and we get 2 anions from this. All right, now you probably are thinking, this is a really long way of showing this, and it is. We learned earlier on a quicker way of doing this. There's a different periodic table where you can just simply go through and figure out what the charges are based on their column. Column 1 always is going to have a +1 charge. Column 2, when in a compound, is going to have a +2. 3 for boron's column, and then -1, -2, -3 for those columns there. without having to go through all of this. So it's a much quicker way, and we can just say, all right, sodium with a +1, chlorine with a -1, they've got the same positive and negative charge, so just put them together and we get NaCl. Or down here, magnesium, again, we said had a +2 charge, and chlorine has a -1. Well, there, that doesn't work out as far as equalizing the charge, so we can use that little crisscross trick. It sometimes works. So I need 1 magnesium and 2 chlorides. And so we get to the same result. 1 magnesium with 2 chlorines, 1 magnesium with 2 chlorines there. But doing it this way really shows the explanation behind it. Why they're doing what they're doing is because of that transfer of electrons. So that's how we use Lewis electron dot structures and symbols to represent the reaction between or between metals and nonmetals to form ionic compounds. All right.